Right now, if you are standing anywhere near the equator, the ground beneath your feet is hurtling eastward at over 1,000 miles an hour. We don't feel this velocity because humans, buildings, and the atmosphere are all moving together at a constant speed. But consider a scenario where the solid rock layer hits an immediate, absolute break. Under the law of inertia, everything not bolted to the bedrock keeps going. The air would continue its eastward rush, generating supersonic 1,000-mile-an-hour winds that would physically scour the Earth's crust. At the surface, any unanchored structure, from skyscrapers to people, would be instantly launched toward the horizon at terminal speeds. The hydrosphere would retain its forward momentum as well, sending the oceans surging across the continents in a series of unstoppable mega-tsunamis. While this sudden halt is physically impossible, the thought experiment highlights the staggering amount of raw energy locked in Earth's angular momentum, an energy that is shifting and changing right now. This diagram represents the angular momentum budget, sharing the planet's rotational energy between three systems: the atmosphere, the oceans, and the solid crust. A strict law of conservation governs this. If the atmosphere speeds up, the solid Earth must slow down to keep momentum constant. This transfer of energy happens through a mechanical process called mountain torque. Massive weather systems act as literal friction against the landscape. They push physically against giant mountain ranges like the Himalayas to alter the planet's speed. These profiles show exactly how mountain torque forces fluctuate throughout the year. The wave patterns reveal the atmosphere physically manipulating the planet's speed across different latitudes and months. The atmosphere functions as a massive mechanical brake and gas pedal, constantly adjusting the rotation of the solid world we stand on. Rotational speed also depends on the physical distribution of the planet's mass. This is the figure skater effect. Pulling mass closer to the core speeds up the rotation, while pushing mass outward slows it down. Catastrophic geological events violently trigger this effect. Massive earthquakes along tectonic boundaries shift billions of tons of rock, permanently altering the planet's spin. This graph tracks the length of day over time. The jagged, erratic top line reveals that the Earth is undergoing constant, microscopic sudden stops and starts as its speed fluctuates. These unpredictable changes force us to actively adjust timekeeping. Technicians must add or subtract leap seconds to keep technology in sync with the planet's wobble. The Earth exists as a grinding, shifting engine, locked in a continuous, violent wrestling match with its own atmosphere and crust. These rotational forces do more than just nudge the clock. They define the physical structure of the planet. The spin creates a centrifugal force that pushes outward. This force is strongest at the equator, making gravity slightly weaker there than at the poles. This diagram illustrates how the outward push forces the planet's mass to bulge at the equator, making Earth an oblate spheroid. If the rotation ground to a halt over billions of years, this centrifugal force would disappear, pulling the planet back into a perfect sphere. On a stationary Earth, oceans would drain from the equator and migrate to the poles, permanently submerging the northern and southern hemispheres. The final consequence is a silent core. Without a spinning molten center to generate a magnetic field, the surface would be exposed to lethal solar radiation. Our survival depends on the atmosphere, oceans, and crust remaining locked in this compensatory dance, keeping the momentum balanced and the world safely turning.